Hi guys. So in this video, we're going to discuss concepts of work and energy. And we're going to develop these a little bit. So it will start simply. And to be quite honest, in Physics 1, most of the time that's enough. But I want to go through it in sufficient detail that it naturally extends to what you're going to see in dynamics and thermo and in Physics 2 and other places. So I'm going to start reviewing some math, just some things we've seen in other videos maybe, or in-person classes, and then just mostly reminding you stuff that you know, and then remind you of how conservation laws work. And then after that, we will dive into sort of work and energy at sort of a high school level, where everything's nice and constant, and then sort out how to lift things up and use our knowledge of calculus to get an answer. Okay, so work and energy. First off, just a reminder of the formula for the dot product. The dot product between any two things, any two vectors, sorry, is A dot B is the magnitude of A, the magnitude of B, and the cosine of the angle between them. And dot products they know about parallel stuff, not perpendicular stuff. Okay, dot products are zero on perpendicular vectors and is not zero on parallel things. The other thing, and I think I forgot to really emphasize this when we had our video on dot products, notice how, because of the behavior of cosine, if you have two vectors that are where the angle between them is less than 90, the dot product will be positive. So if they're working together, you get positive dot products. If the angles are bigger than 90, you get negative numbers. So if the vectors are kind of working against each other, you get negative dot products. Okay, so there's a minus sign issue, and we've got to keep track of that. The other thing harkens back to what we did way back in the beginning of the course when we were talking about velocity vectors, is how we got into this whole mess. And I was talking about in 3 dimensions, if you had a curve, you could have a little baby step on the curve. And since I tend to call position vectors R in 3D, then a little baby step is like a change dr vector in your position vector. Okay, so this is a little differential sized baby vector. It points along the curve, it's tangent to the curve. And if you were to write it out in 3D, it would be a little baby step in x times x hat plus a little baby step in y times y hat times plus a little baby step in z times z hat. So it would be a mix of all of them if we were wandering around in 3D. Now, in this class, we won't have to deal with this, not really. But you want to have this ability, because you'll see integrals over things like this in Calc 3. In dynamics, you definitely will have this, and certainly in Physics 2. So it's good to just kind of be slightly more sophisticated in thinking about differentials and realizing that you can also have vector differentials, just like you can have coordinate differentials. Just baby steps. Okay. All right. Now, in other videos, we've talked about conservation laws kind of in the abstract, and we've also talked about conservation of momentum, the impulse momentum theorem. And today we're going to start discussing energy, which is in the same kind of philosophical approach to solving problems. It's just a different quantity that could be conserved. And so it has, different times you might go one way or another on trying to solve things. it is always going to be completely consistent with Newton's laws. So it's not like you're going to get different answers from one analysis or another. Usually it's more a matter of one route is just impossible. And so you choose the only method you can. If you're given a choice between two, always remember, if you have a choice between a cookie and a kick in the head, choose the cookie, right? Don't go for a kick in the head if you don't have to. My job as an instructor is, of course, to force you to get a kick in the head sometimes. But if you have a choice, make the right one. All right, so the general strategy for using conservation laws is to, step one, define a system. And step two, study the interactions with the system. And somehow the bookkeeping should work out that the change of something on the inside of the system equals the aggregate interaction with or the total interaction with the outside world. So go back to this picture. We have a system. And then we have inputs and outputs. And we're going to want to say that the change inside equals the total or net or aggregate, or however you want to say it, total interaction, amount of interaction. Okay. So now in this class, we're going to think about interactions which add energy. We're going to say they are positives, and interactions which pull energy out of the system are going to be negatives. When we take, or if you take thermodynamics, it's convenient to put in an extra minus sign just to twist the definitions of things. That way, it just minimizes the number of minus signs you actually have to deal with. So you can say, for example, a car engine which produces, delivers energy to the rest of the car. We want to say that that's a positive interaction. And so, but even though it represents a loss of energy from the point of view of the engine. So, okay, that'll come up in later semesters for some of you. All right, so this is our basic kind of paradigm for how to think about conservation laws. It's really just bookkeeping. Now, we are going to talk about energy conservation. And the problem with that is that people use the word energy all the time. You know, if you go online, you see people talking about magic auras and chakras, I don't know, all sorts of weird crystals and, you know, whatever. All sorts of crazy stuff out there. And part of the challenge, or when you talk to people, is it's hard, you know, without going through physics and math and the full analysis, it's hard to persuade people that that's all crap. And I would say the reason is I've never seen one chunk of energy. I've never held it in my hand. So I know what a car is. And so if some quack starts telling me that I've got a magic car and then they actually hand me a piece of paper, I can say, well, you're crazy. I know what a car is. I've seen it. I've touched it. I've driven one. Energy is not like that. We know energy more by its effects, or we deduce things about energy, but we don't ever touch it and see it. And it'll turn out it's even a little bit more removed from, I won't say reality, but from our everyday experience than momentum was. So that's why I like to start with momentum rather than energy, because I feel like momentum is somehow a little bit closer to everyday life. Even though we use the word energy all the time, we haven't seen it. When I was a kid, I watched Transformers, the real Transformers, not the computer animated movie, I mean real transformers. And do you know what real transformers use to keep them powered? They use energon cubes. Okay? And so if you go back to the 80s and you watch Transformer cartoons, they had cubes of energon, which was their energy. So okay, so it was, then it was sort of a thing you can imagine carrying and seeing. But in real life, energy doesn't have a shape. It doesn't have, it's not material in that sense. It's not something I can touch and taste and feel. We deduce its properties by looking at interaction and by looking at the world. So energy, it's going to have a conservation law similar to momentum. It's going to also be different than momentum in that energy ultimately is going to have more varieties. With momentum, we pretty much just have momentum. Okay, it is what it is. It's just mass times velocity. Apply it for every object. It's simple. With energy, as we develop this concept, we will have kinetic energy, we will have something called potential energy, and then for every type of force that's of the right type, called conservative forces, we'll have a different formula for the potential energy, So, and the energy can kind of slosh back and forth. It can take different forms. And so, even though at a high level, this is all very easy, it's just bookkeeping. In the middle of a problem, it can be a little complicated to keep track of what you should include or not include, or you want to include things once, you don't want to overcount. Things like that can be a little tricky. So you just make sure you do the sapling homework and practice and read the chapters. I'll do my best to go through it in these videos and then in when answering questions online if you have them. Okay, work and energy. So big picture. What we want is define some sort of a system There will be a quantity on the inside called energy. And then you'll have the environment. Excuse me. And you'll have interactions between them. When we had momentum, the word we gave for the interactions was impulse. For energy, the word we are going to use for the interactions is work. Interactions cause work. If you have work, then you must have interactions. That's how that will go. Fine. So that, really I've just changed the spelling. We could still be talking about money in your bank account. It's just different words. But it's the way of thinking about something. Very good. Let's imagine, let's go back and focus on kind of a high school level problem. Let's focus on an object moving along in one dimension under the influence of a single force. And let's go ahead and even guess or say that the force should be constant. Now, energy. Well, if I say, I didn't know, I was just saying we shouldn't think about everyday language, but if I had a room full of kindergartners and I went in and I just ripped open a big bag of marshmallows, and I dumped them out and said, have at it, kids. Being the parent of a kindergartner, this strikes very close to my everyday existence. So what would you expect? Or how would you describe it? You say, man, these kids, they have a lot of energy. And what would you see when you look in on the kids. You'd see them bouncing all over the place. It'd be going crazy. So even though that's sort of an everyday sort of colloquial example, that's kind of what we want to get at. And when we talk about gas particles in this room, air molecules, if they have a lot of energy, then we think of them as moving really fast, jiggling all the way, all around. Incidentally, that's another name. It's called temperature. Okay, we'll get to that next year. So the concept, so we have energy, and I somehow want energy to at least encompass motion. And the more motion, in some sense, then the more I want to say that energy is in the system. Something like that, okay? So I'm trying to, there's a definition, I'm trying to motivate the definition. Ultimately, at some level, you have to just choose a definition. So let's go back and try to pull out what is a possible definition of energy. And then at some point, I'll just have to say that's what it is. All right, so if I have motion along the x direction, I have a cart. And let's just assume that I apply a constant force. And let's assume that the cart has a mass. Well, we've already seen how to solve this kind of problem. Constant force, constant mass is going to produce a constant acceleration. If you have a constant acceleration, you can use kinematic equations to solve it for the motion of this thing. So in particular, if I wanted to, if I had a constant acceleration, I could write down kinematic equation number 3. Which says that the velocity squared equals the initial velocity squared plus twice the acceleration times delta x. All right. So I'm going to kind of massage this in the direction I want. It's not really a definition or derivation. It's more of a motivation. And then I'm going to kind of write it in a form that I hope is suggestive. And then I will try to prove this. Well, then I will prove this using calculus. All right. So here's the thing. I have this equation. And let's rewrite this using force, because I want to think about interactions as being related to forces. So rewrite this using force, and then let's kind of shuffle things around. So I can say the acceleration equals the force divided by mass. Right, that's pretty easy. And then I want to divide everything by 2. So I get 1/2 velocity squared equals velocity initial squared times 1/2 plus force over mass times delta x. All right, that's fine. And then I could multiply everything by mass. So I could get m v squared over 2. And I'm going to go ahead and bring the initial velocity stuff over. So I get minus m v initial squared over 2 equals force times delta x. All right, we're basically there. So this should at least serve as a motivation for why things might be defined the way they are. mv squared over 2 is a quantity. It's going to be defined. It's going to be something called kinetic energy. It's an energy of motion. So when you say that all the kindergartners running around the room have lots of energy because they're moving really fast, this is the thing you're talking about. It turns out it also depends upon the mass. So what I have here, if this is kinetic energy, this would be the final kinetic energy, this would be the initial kinetic energy, this is the final minus initial, so it's the change in kinetic energy, change in energy. Well, using my general idea of a conservation law, the change on the inside of the system corresponds to the amount of interaction. This force times delta X is going to correspond to work in this example, okay? Big blaring sirens here. If I talk to 20 students who took high school physics, I say, what is work? They will all say force times the distance. Fine, that's true in high school level physics, okay? That's not actually going to be the full definition, okay? Sadly, even after talking about it over and over and over, a lot of times, even when I talk to second year students who have done this in multiple different classes, I say, what is work? They will still say force times distance. I don't know why it's so hard to remember that this is high school level, but please, when you get there and I ask you next year, what is work? It's okay to say it's force times distance if the force is constant. When the force is variable, we have to be more sophisticated. Okay, so right now, what we're going to do is define this quantity to be kinetic energy. So let's write that over here. Kinetic energy, and I will just write KE equals 1/2 the mass times the velocity squared. And I'm going to call this work for constant forces. That's not always true, okay? But what I have then is if kinetic energy is 1/2 mv squared, this says the change in kinetic energy equals the work on the system, where work equals force times distance. Okay? So the kinematic equation 3, you remember we didn't really have a version of kinematic equation 3 when we had projectile motion or when we had motion in 3D. The reason is because ultimately it had to do with energy, and I mean I could have introduced this stuff at that point, but I wanted to focus on just solving the kinematic problem, just solving for the motions of things. All right, so this is the work energy theorem for a constant force. Let's apply this for a simple situation. Let's imagine that the force that the hand applies is a constant 5 newtons. Let's imagine that the distance that the cart travels along is 3 meters. Let's assume that the initial velocity is 0. Let's use the work energy theorem to understand how to find the final velocity. I know you can use kinematic equation 3 and get the answer. Piece of cake. Let's change how we think about it though. So let's go through the process. To use conservation law, we first define the system. Well, in this case, the system is going to be the cart. Okay? And then we think about what is the quantity on the inside that we want to study how it changes. Well, in this case, we're going to talk about energy, and specifically, we're going to talk about kinetic energy, energy of motion. Okay? And we want to relate the change in the kinetic energy to the interactions with the outside universe, specifically the work being done. So, after defining my system, then the next thing I do is write down my conservation law. So I write down that the change in the energy, or in this case, I'll just specify the kinetic energy, equals the work being done to the system. So that is W is the symbol for work. Incidentally, it just occurred to me, the units of energy is called a joule. Turns out, when you write it in metric units, it's the same as a Newton times a meter. So just so you know, I should have said that earlier. A Newton meter is the same as a joule. However, when you work a problem, if it's an energy problem, we call it joules. Because it turns out torque has the same units, although it's a completely different thing. Energy is a scalar. I should have also said that. Boy, off my game today. Energy is a scalar, just a number, it turns out, whereas torque will be a vector quantity. So when we talk about torques, we'll say Newton meter, or if you're used to use it, where you're tightening bolts on a tire, you'd say foot-pounds. If we're talking about energy, we say joules. Okay. So let's use this work energy theorem, as it's going to be called, to solve for the final velocity. So when I apply my formula, this says the change in kinetic energy. The formula for kinetic energy is 1/2 mass times velocity squared equals the work done on the system. Well, the work is 5 newtons, and the distance is 3 meters, or the displacement is 3 meters. So I get 5 times 3 Newton meters. And because the initial velocity is 0, the change in velocity in kinetic energy is just the final kinetic energy. So I end up with 1/2 the mass which I did not give you, so I will quickly say that the mass is 1 kilogram. Okay? So 1/2 the mass, which is 1 kilogram, times the velocity squared. I'm trying to find velocity, equals 15 joules. That tells me that the velocity squared is equal to 30 joules per kilogram. Turns out that's a meter squared divided by a second squared. And you take the square root and you get the velocity. The final velocity equals the square root of 30, and it'll come out to be meters per second. And I don't have a calculator right in my hand, but I know that the square root of 25 is 5, and the square root of 36 is 6, and we're pretty much halfway in the middle. So I'm going to estimate this to be 5.5 meters per second. And that's close enough. It's about right. Okay? That's sort of an archetypical example of how you use the work energy theorem to solve a problem. You define the system, write down the conservation law that you're going to try to apply, just like we would have done with impulse and momentum. Then you just mathematize this sort of abstract formula. You plug in the explicit formula of all the types of energy at play. In this case, it's just kinetic energy. And then you work out explicitly the form of work and grind through the numbers. A comment. If the force is helping the object move, so basically if the force is pointing in the same direction as the motion, it's helping the motion, then it tends to make things want to speed up. That means that forces that work with the motion are going to give positive work, whereas forces which work against the motion, they tend to make things slow down. We're going to say that that is a negative work. So if the card had been moving forward say, at the beginning. So the cart had been moving forward, but my finger had been pointing, working against it, bringing it to a stop, then my finger would have produced a negative change in the kinetic energy, and you would have said that that was a negative work. So work, the minus signs on the word have to do not just with the force and not just with the path, it's the alignment or anti-alignment. If they work together, it's a positive work. If they work against each other, bad choice of words. If they orient against each other, the displacement and force, then you get negative work. Something else. I feel like I'm forgetting something, but it'll come to me, I'm sure. Okay, next video, we're going to do more complicated examples. Oh, I know what I was saying. The fact that the work depends upon the relative orientation of the displacement and the force. If the angle between them is less than 90, they're kind of working together, you get a plus sign. If it's greater than 90, so if they're working against each other, you get a minus sign. That's the same pattern we had with the dot product. And in fact, when we work out the full version, or when I give you the full version in 3D, there's a dot product at play. That's why we did all this stuff with dot products. And the other thing I wanted to say is, for using impulse and momentum, you had to have a force applied over an amount of time to get an impulse. For work, you have to have a force, but it has to be applied over a distance. So to have work, it's not enough just to have force, you have to have a force applied over a distance. So as I stand still, there are forces acting on me. I have a weight, and I have a normal force, but I don't have a change in kinetic energy. So there can't be any work at play. And what's happening is, yes, I have a force. Yes, I have a weight and a normal force acting on me, but I'm not moving. I have no displacement. And because I have no displacement, the formula for work is going to be 0. I'm going to get no work. Okay, so see you in the next video.